Good morning. In this class, we will study about thermodynamics, especially adiabatic process. In the previous video, we have studied the isothermal process. There are four thermodynamic processes we have discussed in the previous video: isothermal process, isobaric process, isochoric process, and adiabatic process. In the previous video, we have discussed completely and solved problems on isothermal process. Now, let us study about adiabatic process. It is very simple. It is similar to isothermal process. If you understand, then most of the questions, especially they ask based on the fundamentals. If you memorize, then you won't answer. It is impossible to answer. Therefore, let us understand and try to understand the fundamentals and apply it for various problems. Okay, now let us consider a cylindrical vessel. Okay, consisting of 1 mole of gas or n mole of gas, and it is a non-conducting vessel. You remember, this vessel is non-conducting. It means that it cannot allow heat, or no heat is allowed to enter or leave the system. No heat. Heat cannot enter, heat cannot leave the system. Therefore, Q equal to 0. This is called similarly the piston is also non-conducting. Okay, all of them are non-conducting. Therefore, there is no heat allowed to go inside and to get outside. Okay, what is adiabatic process? Adiabatic process is a thermodynamic process in which no heat is allowed to enter, or get outside. Okay, so naturally Q equal to 0. That is the condition. You remember, for adiabatic process, this condition is very important. Q equal to 0. Okay. Okay, now according to first law of thermodynamics, delta E is equal to Q minus W. In the first video, we have derived this expression, delta E equal to Q minus W. Now Q is 0. Since Q is 0, therefore delta E equal to minus W, that is the work done is pressure volume, mechanical expansion work. Okay, therefore pressure volume work done P delta V. Now, similar to isothermal process, there are adiabatic reversible expansion, adiabatic reversible compression, okay, adiabatic irreversible expansion processes. So, let us first see adiabatic reversible expansion process. Okay, now let us consider here, if the external pressure, for example, the external pressure is decreased by an infinite small amount. The external pressure, for example, the external pressure is decreased. Therefore, what will happen? The piston move. It will do some work. It will do work. That is V delta V. That is the work done by the system. In the case of expansion, the work is done by the system. Therefore, work is negative. Okay. In the case of compression, work is done on the system. Then the convention is work W equal to positive. Okay. Now, as you know that CV, molar heat capacity at constant volume is equal to delta E by delta T. I have explained in previous video. Therefore, delta E equal to CV delta T. Therefore, CV dt for infinite small. For example, in the case of adiabatic expansion, during adiabatic expansion, the internal energy decreases. You remember, the internal energy decreases. It does work at the expense of internal energy, because why the internal energy increases? Delta E negative. Delta E is the internal energy decreases because there is no heat supply. The system does work at the expense of using its internal energy. Therefore, the internal energy decreases. Whereas for compression, while the external pressure is increased by P plus dV, then there will be compression. While you compress the system, the temperature increases. temperature increases, the internal energy increases. The internal energy increases, the temperature increases. Whereas in this case, expansion, in adiabatic expansion, since there is no heat exchange with the system and with the surroundings, therefore the temperature falls down. The temperature falls down. Therefore the temperature falls from T2 to T1, for example. Therefore, for the reversible process is slow process, whereas irreversible expansion is it cannot be reversed back. It cannot be reversed back. But here you can go back to its original state. Here you cannot go back to its original state. Okay, now delta E. This is according to the definition of molar heat capacity. Therefore, CV dt for infinite small change, and you know that delta E equal to minus W. Therefore, minus P dV. Okay. Next, now you know that PV is equal to RT. For 1 mole of this is an ideal gas. We have taken ideal gas in the cylinder. Okay. Therefore, P equal to RT by V. Therefore, P equal to RT by V. It's RT by V, dV by V. Okay. Therefore, I write here. Okay, CV dt by. I am bringing T here, this side. Therefore, CV dt by T equal to minus R dV by V. On integration, that is the temperature falls from T1 to T2. The temperature change. The temperature falls while expansion. Okay, they may ask during adiabatic expansion what will happen to the temperature. In the isothermal process, the delta T equal to 0. There is no change in temperature. Whereas in adiabatic expansion, the temperature decreases. Whereas in adiabatic compression, it is increases. They will ask such questions. They are not in the formula. You cannot use the formula to answer such questions. So you need to understand basically. Therefore, initial temperature, final temperature, and volume. Initial volume and expansion, final volume. Therefore, on integration, you will get this one, Ln. I am writing Ln Cv. I am bringing it, yes, Cv here. I am bringing Cv here. Okay. Therefore, Ln T2. This is a dx. Integral of dx by x equal to ln x. Therefore, ln T2 by T1. I am bringing is according to Mayer's relation, R equal to Cp minus Cv. You know that according to Mayer relation, Cp minus Cv equal to R divided by, I am bringing here, therefore ln d1 by d2. Ln d1 by d2. Now I am removing natural logarithm on both the sides. Okay, this is nothing but, as you see, Cp by Cv. What is Cp by Cv? Cp by Cv is gamma. Cp by Cv equal to gamma minus Cv by 1. Therefore 1. Therefore this will be gamma minus 1. This expression is gamma minus 1. Actually this Ln. Therefore T2 by T1. Okay. B1 by B2. This gamma ln. Therefore gamma minus 1. Because Cp by Cv equal to R. Cv by Cv 1. Therefore I am writing gamma equal to Cp by Cv. Okay, therefore T2 by this relation is very important. See, we have derived why they will ask what is the relation between temperature and volume. What is the relation between temperature and volume? One more question. Tv constant, Tv to the power gamma constant, Tv to the. So you need to how this formula is arrived. For example, from using this formula, the relation between pressure and volume is obtained. The relation between pressure and volume. So now see T1 by T2. Okay, this goes up. V1 by V2 gamma minus 1. Therefore this you bring it here. Tv to the power gamma to the minus 1 and T1 V1 gamma. Therefore Tv to the power gamma to the minus 1. Okay, this is the relationship. This is very, very important. This is a relationship between temperature and volume in terms of gamma. The gamma is the ratio of Cp and Cv. Heat capacity at constant pressure, molar heat capacity at constant pressure divided by molar heat capacity at constant volume. This can be calculated. We have seen in the previous video, in the degrees of freedom, gamma can be, we have calculated gamma. If you go and see, you can calculate gamma by using the degrees of freedom. Okay. Now, what is the work? Now, next, what is the relation between PV to the power gamma? PV to the power gamma equal to constant. Now, T equal to, for example, PV is equal to RT. Okay, you know, 1 mole of an ideal gas, therefore temperature equal to PV by R. You substitute here. Okay, PV by R. So I substituted here PV by R, heat power gamma minus 1. Therefore, gamma, this is plus 1 minus 1. Therefore, this constant, you will take it here. Again, this will be a constant, another constant. Therefore, PV gamma to the power gamma is equal to constant. This is very, there may be several problems asked using this formula. Okay, now what is the work done during reversible expansion process? What is the work done during the reversible? W equal to minus dE equal to, you know that W equal to work done. What is the work done during reversible adiabatic expansion? Therefore, W equal to minus delta E equal to minus Cv dt, because this delta D equal to Cv dt. Therefore, W equal to minus Cv T2 minus T1. During the adiabatic process, expansion process, the temperature falls, there is change in temperature, T2 minus T1. Therefore, Cp minus Cv equal to, you know that R. Okay. Therefore, in terms of Cv, you can write Cv is equal to R by gamma minus 1. Cv equal to R by gamma minus 1. Therefore, Cp minus Cv equal to, and divide this expression by Cv. Okay, and Cp by Cv 1 minus 1 equal to R by Cv. Therefore, what you will get is gamma Cp minus, okay, Cp minus Cv gamma minus 1 equal to R by Cv. Therefore, you can interchange this one, you bring it here, Cv equal to R by gamma minus 1. Okay. So, in terms of the work done, in terms of W equal to NR. Okay, this is for n moles, for 1 mole R. Therefore, for n moles, NR gamma minus 1, that is Cv, T2 minus 1. This is the work done by the adiabatic reversible expansion process. Okay, this is very important expression. Please remember, you can use this formula for several problems. Okay, how it is arrived? For example, how the temperature volume relation. What is the relation? For example, this you see PV to the power PV is equal to, for isothermal process. See, this is adiabatic process, this relation. They will ask what is the relationship between pressure volume for adiabatic process. And for the isothermal process, okay, for isothermal process, PV is equal to constant. See, this is for adiabatic, we have derived now. Otherwise, you don't know how it is obtained. Now, how it is obtained, okay, whereas for isothermal process, PV is equal to constant. Okay, now let us consider irreversible expansion. For example, the expansion, adiabatic expansion is irreversible process. For example, at constant pressure, the pressure in the case of expansion, the external pressure is decreased. The external pressure is decreased compared to the internal pressure. Therefore, there will be slow, infinite small expansion. Okay, in this case, the pressure, the external pressure is constant at constant external pressure. Therefore, W equal to, let us use this expression. Okay, W equal to minus P external pressure V2 by V2 minus final pressure minus initial pressure, final pressure. And again, we know that during adiabatic expansion, there is a fall in temperature. Therefore, Cv equal to T2 minus T1. You know that Cv is equal to Cv. Delta V is equal to P delta V and also Cv delta T. Therefore, Cv T2. This expression is very important for calculate the work done at constant pressure for 1 mole of a gas when it undergoes change in temperature from T1 to T2. Okay, now free expansion. What is free expansion? Vacuum. Suppose the external pressure, if the external pressure is vacuum, it will irreversible. Suddenly it will expand. For example, if the free external pressure is vacuum, then it will suddenly expand. Therefore, P external pressure is 0. If you substitute in this expression, then P external pressure equal to 0, then W equal to 0. Okay, it's similar to isothermal process. Isothermal process also the same. These two are same. This only different. Okay, and similarly, delta E equal to 0. Why delta E is equal to 0? There is no delta T. There is no change in temperature. Therefore, W equal to 0. See, W equal to 0. Therefore, delta E equal to 0. Delta E equal to 0. Then delta T equal to 0. Delta E equal to 0. Then delta T equal to 0. Then delta H equal to 0 because Cp delta T is equal to 0. Cp equal to delta H by delta T. Therefore, delta T is 0. Therefore, delta H also 0. Okay. Now, I have given the relation between pressure and volume. There will be several problems based on this concept, relation between, for example, PV to the power gamma. PV to the power gamma equal to constant. Therefore, P1 V1 gamma equal to P2 V2 gamma. Therefore, P1 by P2 equal to V2 by V1 gamma. Okay. For example, they will give pressure, initial pressure, final volume, initial volume. They will ask what is the final pressure during the adiabatic expansion, during the adiabatic compression. Same expression is used for adiabatic compression also. Relationship between temperature and volume. For example, Tv gamma to remember Tv gamma to the power -1 constant. Therefore, T1 V1 gamma -1 equal to T2 V2 gamma -1. Therefore, T1 by T2 equal to V2 by V1 gamma -1. They will ask the problems by giving, there are 4 parameters, they will give 3 parameters, they will ask what is the other parameter, and also they will ask what is gamma, how they will give everything. You will be asked to calculate the ratio of molar heat capacity at constant volume and molar heat capacity at constant pressure and constant volume. Okay, the important formulae are here, or what are the important formulae? Work done, okay, this one, work done by the adiabatic expansion or adiabatic compression, the sign will be reversed. Work done in the case of expansion, work done by the system, negative. In the case of compression, work is done on the system. External pressure is increased, therefore compression, the sign will be negative, the sign will be positive in the case of compression. And this formula you need to know, and you need to know this one, the conditions. What are the conditions? Q equal to 0. And another thing is maximum work done. For example, this is the curve for parabolic curve. This is a parabolic curve, PV curve for particular temperature, and this is for particular temperature. And this one is for isothermal process, and this is for adiabatic process. For adiabatic process, as you see, for example, the area under the curve will give the work done. The area under the curve. For example, the area under the curve is less, whereas in this case, if you see, the area under the curve is more. Therefore, in the case of isothermal process, the isothermal reversible process, the maximum work is done during the isothermal reversible expansion process than adiabatic reversible expansion process. We will continue with the entropy change, free energy change in the next class. Thank you.